So this is joint work with an exceptional group of graduate students and collaborators here at MIT. So AI is booming. Behind this boom is an explosion in data, compute, and energy consumption. So this is a chart of the total amount of computation used to train language models over the years. And you can see that the rate of growth is staggering in recent years. So computation is increasing by 4.6x a year every year, and that's just for training. Arguably, computation for inference is growing even faster going forward. So this puts tremendous pressure on building scalable, efficient AI infrastructure. In fact, scaling AI infrastructure has become extremely complex. Let me give you an example of LM serving, which actually the previous gentleman was also referring to. So these are systems that take requests from users, distribute them across a set of language models hosted on different GPUs, and collect responses and give them back to users. Building an efficient LLM serving system is not just a matter of plugging in some GPUs into a network. It requires fine orchestration of GPU compute, GPU memory, external memory, storage, and networking. In fact, there are systems challenges at all the layers of the stack, all the way from low-level kernel optimizations of the hardware to orchestration software and algorithms for resource management and load balancing and scheduling. So the systems research community that I'm a part of is intensely working on all of these problems. There are literally hundreds of papers published on system optimizations for AI every year. But it's very hard to keep up with all of this innovation because the design space is constantly evolving with new models and new hardware capabilities. So it's very hard for companies to understand the most relevant optimizations and apply them correctly to their infrastructure. So that's where our work on GLIA comes in. GLIA is an AI assistant for Gen AI infrastructure builders. You can think of it as your AI copilot for the entire lifecycle of designing and operating your infrastructure, from ideation to algorithm discovery. GLIA can analyze telemetry information from your infrastructure to detect bottlenecks and propose optimizations. It can build simulation models and calibrate them to your infrastructure. And it can even discover algorithms that are tailored specifically to your workload and infrastructure. So let me give you an example of algorithm discovery using GLIA in the context of LM serving. And I'm going to focus on this problem of load balancing requests in a distributed inference cluster. So the load balancer's job is to basically look at incoming requests and decide which replica to serve each request from. And it wants to do this in a way that maximizes the utilization of your infrastructure, but at the same time is able to respond to users with low latency. What makes designing these load balancing algorithms hard is that the right policy for this actually depends on the characteristics of your particular workload and application. So for example, if I just look at the snapshot of this system here and I say, where should this yellow job go? A simple policy like join the shortest queue would say that this H100 GPU is a good choice. It has the smallest request queue out of all the replicas. It's also an H100, which should be faster than some of the A100 replicas. But the problem is we don't really know how long these GPUs are going to be busy generating responses because we don't know the response length in advance. So it could be that this H100 is actually working on a very long response, and it's going to delay all the subsequent requests. So we wanted to understand if existing LLMs can actually design systems algorithms, such as this one. And so we created a framework where we can prompt an LLM to give us, say, a load balancing algorithm. Then we take the response and we plug it into a simulator that we built that's going to benchmark it against a variety of different scenarios and give it a score. So that's what we're seeing here. These vertical lines are 3 human-designed sort of state-of-the-art algorithms for this problem. And this is the distribution of scores achieved by solutions proposed by GPT-4o. So you can see out of the box, it's not that good. It rarely even beats the second best human-designed algorithm. Stronger reasoning models are not much better. So this is O3 Mini. This is O1. And this perhaps isn't that surprising. So system design requires its own flavor of reasoning and has its own unique intuitions that these models are not really trained to develop. So GLIA has a number of iterative design procedures where it can use all this feedback from the simulations that it's creating to improve a model's design capabilities. Let me show you one example of that, where we use reinforcement learning to improve a base model as a designer. So here we took an open source, small 3 billion parameter model. And you can see it starts out not being very good at this task. But through the course of this training, it actually becomes a better system designer. So you see these phase transitions where it's discovering new ideas and pushing this performance forward. And at the end of this process, actually, it designs algorithms that surpass the best human-designed algorithms for this problem. And you can actually look at these algorithms. Because it's just code that's being generated, so this is an example of one of the top algorithms. And I'm not going to go through this in detail. But when you actually inspect and look at these algorithms, you see that they use very similar ideas to what a human systems researcher would find. So here it found this sort of key signal for predicting whether a GPU would be busy in the problem that I talked about. So GLIA builds on more than a decade of research in our group on building AI-driven systems for a large variety of use cases, from efficient network protocols to scheduling algorithms for cloud computing and data centers, database optimization, video conferencing systems, and AI-driven simulation. And what we've learned from all of this is that now the technology has reached a point where it's really time for AI to be used in system design. Just like tools like Magic, Spice, and the entire CAD industry propelled hardware design forward in the 1980s, AI system design tools like GLIA could usher an era of exponential improvements in AI systems. Thank you.
So, Mohammad, this sounds very impressive. We are talking about GPUs. One of the things I see missing in this is you're looking at efficiency of where GPUs aren't being used. Where does energy fit into this? Are you tackling that? Because that's a very big component.
Absolutely. So if we're able to say that load balancing problem that I talked about, so if we're able to actually improve the latency achieved by packing things better, for the same workload, we can use fewer GPUs. And we can deliver that workload basically with lower energy. So efficiency and energy are not always exactly the same, but they're very closely related.
Right. Have you tried to determine what kind of efficiency we would be able to derive out of this? What are your kind of calculations?
Yeah,
just give us an idea.
The mileage varies depending on use case, but we've seen cases where by using smarter algorithms, you can deliver a workload with 2x, like less resources, or even more, 2x, 3x. So it sort of really depends on the specifics of the problem.
Because a 2x can be quite exponential for a data center, for example. So it's not a very small, massive number in terms of the inefficiency that exists.
Absolutely.
Right. Any questions from the audience here? Sir?
Quick question. If you consider like prompt optimizing of prompt, because you have a prompt, you experiment and you back and forth, but if you have one prompt, you have one shot, but the prompt is to be quite more expensive and accurate with the demand. So if you consider that part to be part of the optimization, not necessarily LLM itself, but the ecosystem.
You mean prompt optimization for solving the kind of system design problems that we're tackling here?
Solving the energy consumption, when you're using less of the LLM time, if you have one good prompt rather than 10 bad prompts.
I see. That's an interesting. So consolidating kind of your prompts and the. So yeah, that's not something we've explored in this particular research. I think it's quite interesting to consider. Absolutely.
You owe him your first 100 million, by the way.
Sounds great.
Thank you very much.